Hello, this paper presents formal verification of line-following robot control using linear temporal logic. The authors of this paper are Mohammed Karam Moni Rabi, Mohammed Fahd Jubriya, Asiful Islam Bouyon, and Zakaria Mahmood. This presentation will guide you through the key aspects of our work. We'll begin with an introduction that sets the context and motivation for bridging formal methods with robot control. Next, we'll outline our key research contributions, detailing the novel elements of our integrated framework. We'll then dive into system modeling, explaining the robot dynamics and sensor configuration, followed by the problem formulation where we define the challenge using temporal logic. The core of our solution is the proposed control framework, detailing our architecture that integrates LTL specifications with control. We'll then present our simulation setup, parameter settings, and a comprehensive analysis of the results demonstrating system performance. This leads to a comparative analysis against other methods and a discussion of our approach's limitations. Finally, we'll conclude with key findings and outline directions for future work. Let's begin. Autonomous systems are increasingly deployed in safety-critical applications where reliability is paramount. While traditional robotics focuses on performance metrics, and formal methods provide mathematical guarantees, these two worlds remain largely disconnected. We identified four critical challenges. First, the abstraction gap between discrete logic and continuous control. Second, the difficulty of maintaining real-time performance while enforcing formal guarantees. Third, limited integration with realistic simulation validation. And fourth, the absence of provable recovery behaviors for exceptional situations. Our research addresses this gap by developing a framework that integrates linear temporal logic directly with robot control, creating systems that are both high-performing and mathematically verifiable. Our work makes 5 key contributions. First, we developed an integrated control framework that combines LTL specifications with real-time sensor feedback. Second, we provide a formal mathematical formulation of the line-following problem using temporal logic semantics. Third, we implemented a simulation environment supporting both kinematic and dynamic analysis. Fourth, and crucially, our approach provides formal guarantees for recovery behaviors, ensuring the robot will always eventually recover the line if lost. Finally, we demonstrate comprehensive validation on complex track configurations. Our technical foundation combines robotics with formal methods. We use a differential drive robot with standard unicycle kinematics, mentioned in equation 1, where x and y represent the position of the robot, theta denotes its orientation, v is the linear velocity, and omega is the angular velocity at time t, and 3 infrared sensors for line detection. For formal specification, we employ linear temporal logic with operators like always, eventually, and implies. A key specification requires that if the line is lost, it must eventually be found again. The core problem is to design a control law that ensures the robot's trajectory satisfies these temporal logic formulas while handling the continuous nature of robot motion and discrete nature of logical propositions. Our solution is this 3-layer control architecture. The sensing layer converts continuous IR readings into discrete propositions. The logic layer evaluates LTL formulas in real time. The actuation layer executes velocity commands based on the current state. The control strategy uses state-dependent velocity modulation. For example, according to algorithm 1, when all sensors lose the line, the robot enters recovery mode by rotating in place. This design formally guarantees that if all sensors are off, eventually at least one sensor will detect the line again. This approach bridges the abstraction gap while maintaining real-time performance. We validated our approach in Capella Sim with a complex test track designed to stress test the controller for the robot system parameters shown in Table 1. Our evaluation used multiple metrics including tracking accuracy, recovery time, and LTL satisfaction rates. Next we shall see a demonstration video of the simulation to provide the effectiveness of the proposed controller. The results demonstrate strong performance for 88.25-second simulation period, 85.2% tracking accuracy with only intermittent deviations, an average recovery time of just 0.45 seconds when the line was lost, and crucially, 100% satisfaction of the recovery specification. Also, Table 2 summarizes the satisfaction results for key LTL specifications. The controller successfully handled challenging scenarios including sharp 90-degree turns, intentional line gaps, and complex alternating curves. In all cases, the temporal logic properties were maintained. When compared to alternative approaches as shown in Table 3, our method achieves higher accuracy than vision-based and neural network controllers while providing formal guarantees that these methods lack. However, we acknowledge several limitations. The binary nature of our sensor readings limits fine-grained control. Recovery paths, while guaranteed, can sometimes be suboptimal. And we need to investigate the scalability to more complex temporal specifications. Despite these limitations, the framework provides a solid foundation for verifiable autonomous navigation. In conclusion, we have successfully integrated temporal logic with real-time robot control, achieving both high performance and mathematical guarantees. Our framework provides a foundation for building autonomous systems with verifiable safety and reliability properties. Looking forward, we plan to integrate analog sensors for finer control, deploy on physical platforms, explore multi-robot coordination, and handle more complex temporal specifications. The development of formal verification of robot control using linear temporal logic is an ongoing process, and we welcome any suggestions or insights. If you have any questions regarding this work or are interested in collaborating on future research in this area, please feel free to contact the authors via the provided email addresses. Thank you for your attention and interest.